Okay, this is a redo of a previous version. I think this is going to be better than my previous version of part 10. We're going to take a little detour, but it's going to be very, very relevant. The motivation is this idea that we want to find a place, a sort of more natural place, and something that doesn't explicitly mention infinite ordinals, where a function of this amazing growth rate, f epsilon naught, actually occurs. If we can do so, then that'll tell us something about what can or cannot be proved in piano arithmetic, as it turns out. It'll show us, basically, it'll give us a theorem that is true from a more sophisticated perspective, or the more powerful theory, but can't be true in piano arithmetic. Well, to start out, I'm going to produce something that doesn't grow as fast as this guy, not nearly. It's still pretty fast growing. And it's a toy model of the real thing. So the real thing is going to be called the Goodstein sequence, and this is the weak Goodstein sequence. So here's the rules. We start with a seed number, and then we write it in base 2. And then we repeatedly do the following thing. We increase the base by 1 in the expression, and then you subtract 1 from the number, and you rewrite if necessary. And I'll explain this with the examples. It's better just to look at examples. Repeat, and if perchance you get to 0, you should stop. What we're going to see is that that's going to look pretty unlikely at the start, because these numbers are going to grow pretty quickly. So here's one example. Suppose I say the n equals 8 is the seed value. So n is equals 8 is the first number in the sequence. I've got to keep track of the base as I go, and I want to keep track of the number. And so what we do is we write 8 in base 2. So if we write out very explicitly, that's 2 to the third. Or if we write out with a little subscript 2 for the base, that's 1000 in binary. Okay, so here's what we do. What we'd like to do is just go up to this, 3 to the third minus 1. But that's not legal. You can't use negative numbers in these kinds of, in a ternary expansion. So you have to rewrite it. So instead of just changing the 2 to a 3 and writing 3 to the 3 and then subtracting 1, that ends up being 2 times 3 squared plus 2 times 3 plus 2. So it's 222 base 3. It's sort of like a 999 phenomenon. If this were in base 10, it would be taking 1,000, making 999. Okay, so that turns out to be 26. Okay, not a staggeringly huge number by the standards of these videos, but still. Okay, then we up the base again. The 3's turn into 4's. This one, notice, this one is the units digit. And so it doesn't have a 3. It's not in front of a 3 to a power, and so there's no 3 to change to a 4 here. What does happen is that gets decremented by 1. In the compact notation, 222 base 3 has just become 221 base 4, which is 41. Then we can do it again pretty smoothly. Change to 5. And I'm going to start focusing on the compact notation, but if you want it really written out, I'll keep doing this for a while. It's going to be 220 base 5, which turns out to be 60. Then we get a crisis again. We'd like to write it as 2, 2, and then a minus 1 base 6. That's not legal. So it actually has to be 2, 1, 5 base 6. So that 5 is appearing because it's 6 minus 1. I had to cash out a 6 for 6 units and then take away a unit. And that's 215 base 6. That turns out to be 83. Up to base 7. Now this is smooth, not a crisis. Just 2 times 7 squared plus 1 times 7 plus 4. That's 214 base 7. That's 109. No crisis. Okay. So this is going to take a while to figure out what happens if we do every single base. Okay. So what I just want to do that as an example, just a few out explicitly. But now I'm going to come back to the absolute simplest seed. Well, except n equals 0, I guess. Seed n equals 1. In base 2, that's just 1. And then I up the base, but that doesn't do anything, and I subtract 1 and I get 0. I'm done. And what I want to keep track of in all these examples is how long the sequence happens. And so that's kind of a hint that, in fact, these sequences are always going to go to 0, but it's not going to look like it. But in fact, and we'll see why they always go to 0 by the end of this video. Okay, or maybe the next video. Length of sequence equals 2 here, and we're done. Okay, what if we start with seed n equals 2? Oops, let's not distract ourselves with that stuff. See if I can get that. Okay, that's not very good. Let me just kind of pull it down a little bit. Okay, well, you're going to be distracted by this. Anyway, seed n equals 2. You write 2 in base 2. That's 10 base 2. Now, I'd love to write that as 1 and then a minus 1 base 3, but that's not legal. So it really just ends up being 2 when I subtract. So that's 2 base 3. Now no more crises. 1 base 4, 0 base 5, done. Length of sequence 4. You might have a guess as to the progression of these guys. You might be wrong, although if you're a really good guesser and you've watched the other videos, you might get it right. Okay, I couldn't have guessed it from those. Now seed n equals 4. So I'm just going to look at the base, look at the powers of 2, because pretty clearly those are going to start in the simplest way. Okay, so that's 1, 0, 0 base 2, and then 2, 2 base 3, because I'd really love it to be 1, 0, 0, but with a minus 1 base 3. So it's going to be 2, 2 base 3. Notice that's a little bit similar to this guy. In fact, the 0 here changing and getting a 2 here, that's really the same phenomenon. So we want to think about that. There's maybe some recursion happening. Then 2, 1 base 4, then 2, 0 base 5, then a crisis happens, 1, 5 base 6, that might look familiar, 1, 4 base 7. Now I'm not going to write them all down. We can tell the next crisis is going to happen when I've subtracted 4 and then 5 from this, or in other words, when I've added 4 and then 5 to the base to get the 12 here. So the crisis really happens at this level. This I wanted to write down because this is right before the crisis happens, but that's not that interesting. It's right after the crisis happens that's interesting. So now the base is 12. I'd like to write it as 1 minus 1 base 12, and that's not legal. I have to cash out my single 12 unit coin for 11 singles because I've lost 1. Here I'm starting to put parentheses and commas in here because when the base is a double-digit number, these guys could be 2-digit numbers, and it's going to be completely ambiguous if I don't put commas in. Okay, so now what's going to happen? Now, this is just an ordinary number. Whenever you get to this, where this number is actually less than the base, it's just going to trickle away. There's no increase, there's no effect of upping the base, it's just going to die. And it's going to die in exactly 11 more turns. And so I get to base 23, and I'm done. And I don't know why I have that leftover row. The length of the sequence is 22, 2 through 23. And so there's 22 things. Okay, might be hard to guess where that 22 comes from, but the next one we're going to be able to see what's going on, I think. And then I'll go back and rewrite what this 22 looks like. Okay, so here's seed n equals 8. Okay. Okay, yeah. Let me hide a little bit of stuff right now. So I've got 1, 0, 0, 0 base 2 for 8. Now the same phenomenon happens. A crisis happens right away. I want to go to 3 to the 3, but I have to subtract 1, so it's really 2, 2, 2 base 3, which is 26. Then 2, 1, 5 base 6. Ooh, I skipped. Well, right now, from now on, without even putting dot, dot, dots, I'm just going to skip to after the next crisis. That's the interesting ones. So this 2 is going to disappear in 3 more turns, and it will have gone to the -1 stage in exactly 3 more turns, and the base goes up by 6. Now, I've got a 5 here. Okay, that gives me a little breathing room, a little time to just subtract, but how many? When this turns into a -1 is when the next crisis will have already occurred, and so that's when the base has gotten up to 12. So 2, 1, 5, 6, okay, the 2 is still safe, but the 1 has now been cashed in, and this has turned into the base -1. It's an 11. Okay, 299, moderately big, but not super huge. Okay, but now it's going to start getting big. Okay, the next crisis is going to happen when I subtract 12 from this. Notice that's exactly this number. So when I double the 12, I'll get the next crisis. And so 2, 0, 11, and it's a big crisis because it actually starts eroding the number in front of the 24 squared. So notice, even though these numbers are getting bigger because the bases are getting bigger, and pretty soon, if you look ahead to here, it's going to get very big, I'm eroding gradually the security of this thing. I'm sort of eroding into the structure. Even as the numbers are getting bigger, I'm working my way into the structure, slowly but surely. So if I double again, I take 24 away from 23, I get a -1. That's this crisis here. And I ratchet down the 23 to a 22. So this is really crucial. We double the base each time to get to the next crisis. It's about repeated doubling. And if you think about the fast-growing hierarchy, that might give you a hint of what the pattern's going to be here. So, okay, so now I can kind of cut to the chase here. I can say, well, how many times am I going to need to double to decrement this 23 to 22 to 21 to kill that guy, in which case this guy's going to have to get cashed in. Okay, I'm going to have to take 24, which is where I was here, and I'm going to have to double 24 times, because it's really when this becomes a -1 that is the crisis really actually occurs. So let's call A the number 2 to the 24 times 24. And again, if you think about the fast-growing hierarchy, that should look familiar. So in base A, this pretty big number, it's going to be A minus 1, A minus 1, the two-digit number, the biggest two-digit number, base A, which is really big. Okay, so that's just A squared minus 1 written in a legal way. Okay, so now what's going to happen? I've got an A minus 1 here. It's the same reasoning. When I've got this second digit, like this, these 23 and 22, I knew to decrement this by 1, I've got to double the base. Okay, so I've got to take this A minus 1 all the way down, and I can't quite get it to minus 1 because it's the highest digit. But what's going to happen? I'm going to, let's double A minus 1 times, and that's going to make this go away to 0. It's going to turn it into a one-digit number in a huge base. So I double A minus 1 times, so the base is now 2 to the A minus 1 times A, and that's gone away. Now it's just a two-digit number. Okay, this has exponents in it, but it's a little misleading. This is simply a one-digit number in this base, because this number is less than this guy. So this is just after the last crisis, the number is now less than the base. This is a really huge number. I'm not going to write it out in decimal anymore. Not too surprising. I haven't written out anything decimal for quite a few videos now. And it's this magic base, almost magic base, minus 1. Now there's one more step to remaining, which is to just decrement that guy by 1 by 1 by 1 by 1 by 1. So I obviously need this many steps to kill it, of subtracting 1. If you double this, you get 2 to the A times A, but then I don't quite need that many steps, because if you carefully figure it out, it needs exactly this base to where, and I've just forgot to kill these guys. These guys are 0. I was copying and pasting and forgot to change. Zeros. And then this is just an even bigger number. Okay. Actually, no, I'm sorry. It's 0. Just kidding. Okay. This is the biggest it gets, and then it goes down, 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 down. It just takes a long time, and it goes down to 0. Okay. So let's look at the length of the sequence. So I'm going to call f of n without any subscript. It's not one of the fast-growing functions yet. F of n is supposed to equal the length of the sequence with seed n. Okay? And this is called the weak Goodstein function. So secretly, what we're mostly interested in this sequence for is to create this sequence. So hopefully you're getting convinced that this sequence has some really interesting behavior, that it grows and grows and grows and gets really, really, really big, even from a starting small seed, and then eventually ratchets down to 0. And if you give somebody just the first 10 or 100 or even 1,000 terms of this sequence and don't tell them what the rule is, they're going to very confidently predict, hey, this thing's going to infinity. Any sequence I've ever seen that's this big, it goes to infinity. But it's not. It actually eventually plateaus and then goes back down to 0. Okay? And so, in fact, if we believe that that's always true, and in the next example I think we're going to see even more confidently why that's always true, then the sequence has a finite length for any seed, and we can call f of n to be the length of that sequence. And that's what we're really most interested in, is this function that gives the length of the sequence. Okay? And let's look at the pattern here. F of 8, that's the length of this sequence. What was it? It's take this base and then just subtract 1 to get the length of the sequence, because we started with base 2. So it's 2 to the A times A minus 2. But what was A? Okay. A was itself a 2. It was 2 to the 24 times 24. Okay. So let me expand that out. It's 2 to the 24 times 24, and then times 2 to the 24 times 24, and then minus 2, but the minus 2 is not particularly important. Okay. And what is 24? 24, let me just do this. 24 has a similar structure. 24 is 2 cubed times 3. And so I'm going to just put everywhere I see a 24, I'm going to put a 2q times 3, again utilizing cut and paste because that's a way to do recursion. That looks very interesting. It says take 3 and double it 3 times, and then take that number and take 2 to that and multiply it. And then take that 2 to that and multiply it. Huh, that should look familiar. I'll let you think about exactly what that is in terms of the fast-growing hierarchy. But I'll do one more example. Let's look at seed 16. And we already know this number 2 to the a times a is interesting. Let's call that b. And that's just exactly f of 8. The length plus 2 was very close to just f of 8. Okay. So I start out with 1, 0, 0, 0, 0, base 2. And then I get 2, 2, 2, 2, base 3. From my first crisis, it would be 3 to the 4th minus 1. And then I'm going to skip all the way to b. Because what's happening, here's the crucial observation of a lot of this, I know what happens to 2, 2, 2, base 3 as I go forward. That's exactly what was happening up here. That's the sequence for 8. And I know exactly when that part of it dies. It dies at, it goes to 0 at 2 to the a times a minus 1. And here's where the minus 1 doesn't actually turns out not to bother us. When would the crisis happen is when this would go to minus 1. That's when a crisis happens and starts making us have to change in this 2 in the cubes digit. Okay, so we're going to have to change that out exactly at 2 to the a times a, which is called b. Okay, so we're going to get this gigantic number, 1 times b cubed plus b minus 1 b squared, etc. So it's just 1 comma b minus 1 b minus 1 b minus 1 in base b. It's a ginormous number. That's our substitute for we would like to keep 2 of our b cubed coins and just owe somebody one unit of money, but we have to change out our money. Okay. Then what happens? Okay. Well, we need to let's see. We need to kill this digit. So now let's think about what did it involve to kill this digit? Not this one. This one goes down just by ones every step. This one went down when I doubled the base. This one went down when I doubled this many times. Let's go back to 8. And remember, to kill this digit, like take this 1 and make it a 0, we had to take 24 and double it 24 times. That was the source of this a. So we take a number and we double it that many times. That should sound extremely familiar from the fast-growing hierarchy. It is exactly one of the functions from the fast-growing hierarchy. Okay, so let's continue, and I'm going to start using the fast-growing hierarchy. So recall that f2 of n was equal to just 2 to the n times n. It was the repeated doubling function, or 2 to the n. Okay, and so this big base b, in order to kill this digit, or even just to take it down by 1, not kill it, but just take this down by 1, I have to ramp up the base to 2 to the b times b. Okay, and then I'm going to have to do it again. Okay, so I'm going to have to take this big number and double it that many times, 2 to the b times b many times. Well, that's exactly take f2 of b, which is this number, and put it into the f2 function again. So that's f2 squared of b. That's interesting. I'm repeating an f2 function. That is going to lead to an f3 very soon. So I keep going down, down, down. Now finally, how many times am I going to have to do this to kill this b minus 3? Well, I started with b, and then I actually want to kill it and even make it a negative, and so that I'm going to have to cash out this coin, the 1 coin, in this b cube slot, the base cube slot. And I'm going to have to do this operation b many times. So I started out with this, and I now know what it means to decrement this digit. It means do the f2 operation, and I have to do it this many times to make this become a minus 1 and provoke the big crisis. And so what I'm going to end up getting, now here I've deleted this because it gets too big. This is useless because I'm not going to be able to write down the decimal. I've just got the compact form. This has become a 0. This is now f2 repeated b many times of b minus 1, and then just repeat. And here's a note. Well, f2 repeated b many times applied to b, that's the definition of f3 of b. And remember, b was really defined in terms of repeated stuff as well. So f3b was exactly f3 of 3. Let me actually write that down. So b, so here's giving away the game here. B is just f2 of a, okay? But a was 2 to the 24 times 24. That's an f2 function as well. That's f2 of 24, but that was 2 to the 3 times 3. And so what do we get? That's f2 of f2 of f2 of 3. That's f2 repeated 3 times. Applied to 3, that's f3 of 3. Okay. And so b is none other than something from the f3 version, the f3 function, the third version function in our hierarchy. And so I've gone ahead and put that in here. That's really this b is f3 of 3. So f3 of b is just f3 squared applied twice. f3 of f3 of b. Of 3, sorry. Now we're not quite done. We need to take all this stuff and kill it off again. So how many times do I need to do that? I need to take this number. This number tells me how many times I have to do the f2 function to get the base up to something where it will work. Now I don't have to quite go that far because that would actually provoke the next crisis, which would be beyond 0. So I'm going to have to subtract 1 here. But I take f3 of b, which is basically the base up here, otherwise known as f2 to the b power of b. Okay, so I take f3 of b, which is really f3 squared of 3, and I take f2 that many times. Okay, so the punchline is that the base, even without this subtracting 1 thing, I've done the f3 function now 3 times to 3. Well, what is f3 cubed of 3? f3 cubed of 3 is the definition of f sub 4 of 3. Okay. And so the length of the sequence, I have a subtract 1 from the base, and then I didn't start at 1. It's actually just these guys minus 2. Okay. So here's what we're getting. That's f4 of 3 minus 2. The length of the sequence here, this was none other than f3 of 3 minus 2. And the length of the sequence here was f2 of 3 minus 2. f2 of 3 is just 2 to the 3 times 3, which is 24, and then minus 2. And in fact, this even works. This is f1 of 3. Double 3 and subtract 2, you get 4. And this is f0 of 3. Just add 1 to 3, but then subtract 2, and you get 2. So now we see the pattern. Okay. So at least 4 seeds that are powers of 2, and hopefully those are going to be representative, and they are. Then we get f of 2 to the k. Our length of sequence Goodstein function is just the kth function in the fast-growing hierarchy applied to 3 and then subtract 2. Or in other words, f of n is going to be, let's say roughly, because we only did it for these special values, is going to be f sub log 2 of n. You take the log base 2 of whatever this number is, and I guess we're going to have to use probably like a ceiling function or something. I think I have that somewhere. I would say probably a ceiling here. Okay. And I'm not going to worry about the minus 2 because these are all approximate. Okay. And that is less than f sub that expression of itself. So I want to just express this in terms of one single f function, and that's the great thing about the fast-growing hierarchy. Even though this says which function I choose depends on n, oh, that's exactly the point of the diagonalization trick. So let's just replace 3 with log 2n. Hey, that's, oh, and that needs a ceiling as well to make it an integer. It's not a big deal. And that's exactly f sub omega of this quantity, ceiling of log 2n. So that's an estimate for how fast this function grows. Hopefully you can see that it really is well defined, that even though this function gets to huge numbers and these bases get so big and the function takes so long to complete, that gradual erosion really keeps going. And this recursive procedure, even though it takes a tremendously long time to kill the big digits, the digits with big powers, they do eventually die. So this is a natural, a somewhat more natural occurrence of this f omega function. Okay. And what does it mean about arithmetic and proof theory? I'm going to stop this long video in just a minute. For arithmetic and proof theory, it turns out that you can really prove, I've just been claiming, and you can kind of see how this might be turned into an induction proof, that piano arithmetic, basically ordinary induction, and that means non-transfinite induction, basically, can prove that this sequence always goes to 0. And hence that the function, the weak Goodstein function, is well defined. That no matter what you put in, the definition will actually produce a number. And it's going to be grow really fast. So that function doesn't grow too fast for piano arithmetic to handle. But it's pretty darn fast. In the next video, we're going to get the full strength Goodstein function, and it is truly amazing how fast it grows. And it's going to be something where it grows so fast that piano arithmetic is going to be outclassed. And ordinary finite induction will not be able to prove that the sequence terminates, but a more sophisticated method from ordinals and set theory can easily prove it.